that's okay. You guys, everything else running smoothly. All right. Yes, sir.
On 17, I'm just not sure why the left half of the parabola isn't included.
I don't know. Can I read it? So, let R be the region bounded by y equals x squared. X equals what? Hold it. X-axis. Y-axis. I said y equals x squared. X equals 1. Now, let me do that correctly. I said x equals 1. And y equals 0. So you guys, let's take this region, bounded by these three equations, these three curves, and rotate it. I forgot about which one.
No, don't do that.
Yeah, don't do any of it. Item against the bounded region. I think when you look at this parabola, you look at this vertical line, you look at the horizontal line in blue, I think there's only one region bounded by those three equations, and I think it's this region. That's the only region that's not unbounded going in some direction. Did you guys see my point? So I do think necessarily in this example, not that I finished reading the question, who cares what line I'm revolving about? I think this is the one region revolving about whatever the next line is going to be. Makes sense? It's just a question of being careful with your equations. Nothing more.
Can you follow through and just kind of step-by-step on for the revolving around x negative?
I'll do whatever you like. And so I've got the line x equals -2 right here. But you guys, in this question, my arm's being twisted. I'm being told to use the cylindrical shell method to take this bounded region, revolve it about the line x equals -2, and compute the volume of the corresponding solid of revolution. Well, to do that, if you guys don't mind, I'm just gonna concentrate on one cylindrical shell. I don't know how to do this. Is that a vertical or a horizontal rectangle?
Vertical.
Definitely vertical. So that when I do revolve about the line x equals -4, sorry, I meant -2. I'm going to get another triangle over here. See that pretty triangle? And here's a corresponding cylindrical shell I got. Being a little sloppy. By the way, just to keep things straight, do you guys mind if I label this part right here on the black curve to be x of I, comma y sub I? Now I think in generating an integral that will indeed give me the corresponding volume. I will generate an integral that looks like the volume is equal to 2 times pi times the integral from I don't know where yet, of the radius of the cylindrical shell times the height of the cylindrical shell times the thickness. I can spell thick, I really can. Of the cylindrical shell. And if you guys don't mind walking backwards, I think the thickness clearly is going to be a small direction in the x direction. Small dimension, I should have said, in the x direction. Which means everything else I put in here better be in terms of x. And I think the height of the cylindrical shell is nothing more than the corresponding y value on the graph. I think the height of the cylindrical shell is just y sub I. It's just a y sub I on the graph of that equation. And I think in terms of my variable integration, the variable to which I pledge my allegiance, I'll rewrite that y in terms of x. Continuing to walk backwards, I think I need to identify what the heck the radius is of that cylindrical shell. And looking at my pretty picture, I think the radius of my picture using a green pen. Aw, somebody tricked me with colors. I said green pen. I think the radius is right. And you guys, I'm sorry, but I need to bore you to death. I want to impress upon you how lazy I am to compute this radius. I think it's just simply length on the x-axis. And to compute that length, I will identify the large x value, which is x of I, minus the small one, which is -2. I think the radius of the I slice, of the I cylindrical shell, I should say, is x of I minus -2. Or x of I plus 2. Or when I take the limit of the sum, that's a Riemann sum, of course, I think I'm going to get a x plus 2. That'll be the radius. And did I forget things, you guys? I guess I forgot my bounds of integration. They go from where to where? Why? That's the word why. Why?
It's the, where your function is beginning and ending, or your bounded region is beginning and ending.
So it's because my bounded region begins at y equals 0 and ends at y equals 1.
No, the respect to x,
How do you know?
because that's the length of that's the slices you're taking.
All right, I like that. Is where all the vertical slices are stacked from left extreme to right extreme, or how about looking at the flag to which I pledge my allegiance? I think the most extreme values for the x variable are going to be from 0 to 1. And I admit, goofy example, if you made a mistake and looked at the extreme values for y instead of x, you would have got the same balance just because the example is so nice. That's why I'm just trying to hit you up, saying you really get it from extreme x values, from here to here. Now you guys, I want a yes or no answer. Truly, is this an absolute piece of cake to evaluate?
After
Yeah.
you distribute.
Yeah, after you distribute, you just integrate term by term. Do you have to distribute?
Yes.
What do you mean no? Why not?
You can do sub.
What do you sub work?
No.
Yeah, I don't think it would work that smoothly because I threw x squared as 2x, but I got an x plus 2. So I do think in the end I'll have to split up. Do you guys mind if I go?
Yeah. Now, when you're finding the radius, I find myself having trouble doing that. Is it always the whatever whatever axis you're on, plus the I can't say always because that might not be true, but whatever axis you're on, the distance from there to whatever axis you're spinning around?
No. Because I think if I were to revolve about the line x equals positive 2,
Yes.
it would really be the x value on terms of the line of spinning about.
So there'd be 2
minus
minus
the
x.
I think it gets reversed. So instead of memorizing something, I always play this game. I just simply say, who cares what's to the left? Who cares what's to the right? You just take the largest value in the x-axis, that's to the right. Subtract off the smaller x value, that's to the left. And if the line were here, I take that x value minus this one, because I take the largest minus the smallest.
And your function plays no role in that particular part?
None whatsoever.
Okay.
None whatsoever.
So when we're rotating about an axis that's not the x or y axis,
Yes.
should we always use the cylindrical shell method?
No, I don't think because you're revolving around a non-axis that it necessarily implies you should be using the cylindrical shell method. I think to answer your question, which one you should use, would be to identify what the integrand looks like. Maybe another component of your decision. Maybe using one technique over another allows you to have only a single integral as opposed to maybe 2 or 3 or 4. So I think there's a couple things that come into play when you're making your decision what technique to apply. But given that it's a line I'm rotating about that's not one of the axes, is not a component of my decision making. Because I don't think that necessarily implies you should be using cylindrical shell.
So in this example, x plus 2 is the radius. What would be the radius in the washer method? How would we?
Oh, you guys, this question is too nice. Can I?
Please.
You said you're okay with what I did, right?
Yes.
So can I go back to this picture? Let's just pretend we were to employ the washer method to actually compute this integral. Before I erase it, what changes?
Your
Rectangle is going to be horizontal, isn't it? Because I'm still rotating about that line x equals -2. So you guys allow me, let me clean this messy picture up real quick. And with my red pen, let me sketch in a horizontal rectangle. And I'm going to rotate that about the line x equals -2. And there's the corresponding washer. Now, in setting up my integral, I think, just kind of loosely, I should be saying the volume is going to be computed by looking at pi times the integral from I don't know where to I don't know where yet, of my outer radius squared minus my inner radius squared. Can you guys appreciate how lazy I'm being at the ink board? I'm not identifying the functions or what the radius is yet. I'm just schematically mapping out what the heck I'm going to be looking for. Oh, by the way, because I'm using the washer method and rotating about a vertical line, I'll be integrating with respect to how do you know that?
because that's the delta y of your Riemann sum.
Okay, I'll buy that. My infinitesimally small dimension is in the vertical direction. It's a delta y before I take a limit of the Riemann sum. But that implies when it comes down to the right. Did I say something wrong? I did, I apologize. Because when I take that horizontal rectangle and rotate it about this vertical line, maybe now I can identify what the outer radius is. Now watch me. I'm not using my pen. No matter how high or how low that rectangle is that's horizontal, is the outer radius always a fixed constant?
Yes.
Yeah, it is. Let's talk about what it is. This line's located at where? X equals 1. And so I think this large x value minus the small x value is going to be
You mean your
1 minus negative 2. That's just positive 3. So I think no matter how high or how low that particular horizontal rectangle is located, I think the outer radius is going to be 3. As far as the inner radius is concerned, let's play. Depending if my rectangle's high or low, I think the inner radius changes. So this time around, if you guys allow me to allow this particular point to have coordinates x sub I comma y sub I on the graph of this equation, then I think the inner radius is nothing more than the x value of that point minus the x value of this point, but that would be square root of 2. Did you walk a little too fast? I think it would be x sub I minus negative 2, which is x sub I plus 2. You square them individually. Oh, nice job. But since I think that the radius, inner radius is going to be x minus negative 2 or x plus 2, we'll give x some alternative name. Because I'm integrating back to y.
root y plus 2.
See the difference? You guys okay with that? Please tell me if you're not. Oh, I messed up, didn't I? I forgot my bounds of integration. Can I just copy it down from up here? No, I can't, because that was a range of values for in the x direction. Now I want a range of values in the y direction. I admit, this example's kind of goofy. They end up being the same, but I got to be careful in general.
Now, follow-up question.
Yes.
When you're to exploit symmetry in any one of these problems, what defines the fact that you would be able to do that? Is it the fact that the functions in the middle are even, or is it say the two functions that are encompassed by that give you the length of the rectangle, or is it because there's some visual symmetry within the actual problem?
Good. I disagree with what you said first. I think the fact that you might have symmetry in computing the volumes of these solids of revolution doesn't necessarily tie into whether the original functions are even or odd. I think, better yet, I think instead, exploiting symmetry to compute the volumes of these solids of revolution really means you're identifying some symmetry in the picture.
Okay.
For example, watch this picture. X-axis, Y-axis. You guys, I can't draw very well. What you see here is a mirror image of this about some vertical line. If I asked you to rotate this shaded region about the y-axis using any technique you darn well please, can you exploit symmetry?
No.
See, I don't think you can. I didn't think I could exploit symmetry at all there. What if I asked you to take this two-dimensional region and revolve it about the x-axis with whichever technique you darn well please?
Yes.
I could do symmetry there. Yeah, I think maybe I could just cut it in half and compute half of it, and then double the result.
Okay.
But notice that in this example, neither this curve nor this curve represents necessarily an even function.
I got you. So if there's a gap, really.
And I still think it has a big gap.
Well, I mean, when you spin it around the y-axis, there's a big.
All right, I'm going to change it and make it more interesting. Okay, hold that thought. Hold that thought. And I mean to imply symmetry, you guys. Now, if you're going to revolve that about the y-axis with whatever the heck technique you darn well please, any symmetry?
No.
I can't hear you.
Yes.
Yes, there is. After all, David, just taking the upper half, rotating about the y-axis. Same as taking the bottom half.
Oh.
So if you want, not that you have to, but if you wanted to, you could have exploited symmetry there. I was nervous because in the last example I heard you say, oh, gap, I can't use symmetry notions. Not necessarily, I can move there.
So in this, I'm just trying to find a pattern. In this case, it's
What?
it's got to be an easy way to this.
There is, you just kick back, put your feet up, look at the pretty picture.
Of course. But in this case, it's reflective about the x-axis. So there would be symmetry in regards to that if you're spinning around the y. But if it was only the top portion, there would be no symmetry because there would be no reflection.
True.
Okay. Always?
I can change it. But I'm nervous. I heard you say, you know, there's symmetry with the x-axis. I know when I rotate it on the y-axis, more symmetry. Not necessarily. Look at this one. Now rotate about the y-axis. I'm shaking your things. I hate to have you say, oh, I'm going to memorize some case scenarios for which I can exploit symmetry. I just don't have any. I keep violating what you say by showing you, shaking up, suggesting.
Well, it's not reflective about the x-axis, so there's no symmetry there.
True, but if I'm going to revolve this two-dimensional region about the vertical y-axis, there is symmetry, and I can exploit it. I can just integrate from, say, I don't know, bottom to top. I'm not trying to.
I'm just not going to use symmetry.
You guys, can I close this? Well, if you have no questions, that means you guys get to show me what you know.